So purpose of this lab is that we want to essentially test and confirm a relationship that we've been talking about quite a bit already, and that is that work equals force times distance. Okay, we want to check out and make sure that that formula is verifiable in a lab situation. Okay, so we're going to run a lab where we're going to use a rubber band and a spring scale. A spring scale can measure force, okay, to see if we can get kind of the numbers we should for work done when we pull the rubber band back. So when we stretch the rubber band a certain distance, what force is going to be used for that, and then are we going to be getting the right numbers for work as we go along, right? So that's kind of the premise of the lab. So for our variables here, okay, manipulated, responding, and controlled, okay, so in this lab, we are going to choose the distances to which we are going to pull the rubber band. All right, so we're going to select a certain, probably 5 or 6 of them. Okay, I'm going to take it back to this many centimeters, this many centimeters, this many centimeters, and so on. Okay, and then we're going to measure and record how much force is required to pull the rubber band to those chosen distances. Okay, I think you guys can figure out a couple of them from that. Some things that we need to keep the same throughout all of this. Okay, so the way this lab sets up is we're going to set 2 desks beside each other, right? Because you can't actually use the legs from the same desk. Okay, so we'll set them so that we've got them a certain distance apart, kind of like these 2 are here. Okay, just enough that the rubber band is taut. Okay, that it's not slack and it's not like already ragingly tight. Okay, so it's just so that it's not sagging. Then from there on, the setup cannot change. If anything about the setup changes after that, it could put a different amount of initial tension in the rubber band and our results will be skewed. So that means that we're going to have at least 4 people in a group, because 2 people's job is going to be to sit in the desks and make sure they don't move. Because believe it or not, during this lab, if people are not sitting in the desks you are using, they will move when you start trying to stretch the rubber band with the spring scale. All right, so we need 2 people who are just going to be wait, okay, sitting in the desk and making sure that the desk doesn't move. Okay. We have to also be mindful of a couple of things when we are doing our measurements, and that is that when we're doing our measurement, we probably want to look down from above at the ruler. Okay, we don't want to come in from the side or anything like that, because that could affect our judgment on how far back did I actually pull the rubber band. Okay, everybody all right with that idea? Okay, so a couple of things there. That should give you a pretty good idea of some of our controlled variables for this lab. Okay, for our hypothesis, okay, we want a hypothesis that explains how we can calculate the work done on an object. Okay, so the if part, okay, the if part of our hypothesis should talk about what work is. Okay, and I don't mean if work is force times distance. I don't want that in your if part of your hypothesis. I want a definition of what work is. When we do work, something changes. Have something like that in there. Okay. The and part's going to describe our experiment. Okay, and the then part should talk about, okay, what is our how are we going to be able to calculate the work done? All right, we're recording force, we're recording distance. Okay, we're going to make a graph of force versus distance. Right, is there a way we're going to be able to calculate how much work is done, okay, in this lab from that? Okay, so the then part should talk about how we're going to calculate the work. Okay, now I believe in your lab report already, I have the chart in there already. Okay, and are those the distances I put in there? There's no distances in there? Okay, so here's what we're going to do. We are going to probably not use these distances either. Okay, these distances are just going to be way too far for what we're doing. Okay, so let's just put in the following distances. Okay, we'll choose what the distances are going to be. All right, so obviously when there's when we don't pull it, okay, that'll be 0. Right? But we're also going to have, let's say we'll go with every 2 centimeters. So 0.02, 0.04, 0.06, 0.08, 0.10, and 0.12. Okay, we go much further than that, and we're going to start getting weird results because we will overstretch the rubber band. Okay, a rubber band stretches pretty linearly for a while, and then once it gets beyond its true elastic range, it starts acting funny. All right, so we don't want to get into that situation. Okay, that's good. Now it only goes up to 0.10, then you're good. Okay, so what you guys are going to record then is the force that is read off of your spring scale. Now, we do have a small problem with these spring scales. Okay, it's not going to affect our results terribly. Okay, in fact, it's not going to be a source of error at all. But when we ordered these scales back in 2005 when we moved in here, okay, we ordered ones that measured grams and newtons. Newtons are the units for force. Okay, and oddly enough, the box shows exactly that. A picture of a scale that has grams and newtons on it. Unfortunately, what is in the box shows grams and ounces. Every last one of them. And so we called up the scientific company and said, hey, like, look, you sent us the wrong stuff. And they said, no, we didn't. We sent you exactly what you ordered. And we said, well, you sent us the right boxes, but what's in the boxes is wrong. And they wouldn't refund our money. Hence, we have never ordered anything from them again. Customer's always right. If you ever get into business, remember that. Okay? Because we have the ultimate power to stop spending our money with you. All right, good life lesson. There's your life lesson for today. Okay, so what we're going to do instead is we're going to use the grams to figure out our force. It's an easy conversion. Just take whatever it reads in grams and divide it by 100. That'll be the newtons. Okay, so it reads 400 grams, it's 4 newtons, right? And you just record that in the force part of the chart. Okay, easy conversion. Now, when you start, okay, you'll notice that this, on the spring scale, this little thing here, the silver piece that has the scale on it can move, right? So when there's no pressure on this, make sure that the little tag there is at 0. It's not right now, okay? So I just pull it until it's at 0, and then I can start doing the experiment. Otherwise, you're going to be off by a certain amount every time. We don't want that, okay? So make sure you check that before you start. And then when you're pulling on the rubber band, okay, just try to pull as straight as possible. If you pull at an angle or anything like that, you're going to get some wonky numbers. So try and pull it as straight as possible when you're doing this. Okay. Unlike the diagram in, and just like the diagram in this one, we're going to want both sides of the rubber band in the hook of the spring scale. Okay, so don't just pull one side of it, pull both sides of the rubber band. Everybody with me there? Okay. What if your rubber band breaks in the middle of the experiment? Get a new one and start over. Yeah. Okay. These are all supposed to be exactly the same, but there's no guarantee of that. I don't know why these are all tied together. Just get a single one like this. Okay. If it breaks in the middle of the lab, and it happens occasionally, not often. Okay. But if it does break, then you do need to start over because you have a different rubber band. Okay. And we can't be sure they're all exactly identical. Okay. Plus, you'll have to move the desks, and that's going to throw it off a little bit too. Okay, so just be careful with that. So every group needs one rubber band. They need one spring scale. Okay, make sure, obviously, again, when you're doing this, that you've got both sides of the rubber band in the scale when you pull. Everybody with me there? Okay. Secondly, I do not want to see these shot around the room. Okay, it's all fun and games till someone loses an eye. Then it's a sport. Not really. We're not going to shoot the rubber bands around the classroom. Everybody's good with that. You don't have to be good with that. You just have to do it. Okay. There are 2 kinds of scales in the box. 2,000 gram and 500 gram. Take the 2,000 gram. It's labeled on the top. Okay, so make sure you grab ones that say 2,000 grams, because if you grab the ones that say 500 grams, you're only going to be able to do like 2 of those distances that we listed there, and it'll be maxed out. All right. So if it does so happen that your last distance maxes out the scale, that shouldn't be the case. Then pick a couple of other distances in the middle of the other ones and get forces recorded for those instead. Right? We shouldn't have a problem only going up to 10 centimeters. Meter sticks are here. Okay. When you lay the meter stick down, make sure that the 0 is right in between the parts of the, like right in between the desks, so that when you've got the rubber band there, the 0 is smack in the middle. Right, because you're going to be pulling both edges together. Okay, so make sure the 0 is right in the middle. Okay. All right. For the analysis, okay, there's a lot of writing in here, and a lot of it is kind of unnecessary in terms of what you need to do, okay? So the first thing we want to do is once we have our data, we want to plot a force distance graph. So you're going to need to make a Google Sheet, okay? Plot that information in. Distance needs to be the first column because it's going on the x-axis. Force needs to be the second column because it's going on the y, right? Plot that graph, and then I want you to calculate the area underneath your line. So you'll need to put the equation on there, and just like in your Need for Speed lab, okay, calculate any area under your line. If it's just a triangle, calculate the area of the triangle. If it's a triangle and a rectangle, calculate both, right? That is going to help us to calculate something which you have to figure out in the analysis part of this.
Are you going to have to make separate graphs for every single reading?
No, this graph is of all the readings.
Okay.
Okay, so basically just calculate the area underneath, kind of ignore what it says here. It gets kind of confusing. And then question number 2 is the really important one. So I want to see your calculations for question number 1. And then I want an explanation, a good thorough one for question number 2, where it asks you what the area under the force distance graph represents. How do you know that? Think about what you multiplied together, okay, to get that area, okay, things like that. Then you have your conclusion, so restate your hypothesis, okay, explain whether it's acceptable or rejected, and your sources of error and ways to improve them, and we'll do the class discussion when I hand them back. Okay, one other thing. I set your exam date. Your exam is going to be May 28th. Okay, so that's on the board now as well. Okay, May 28th is going to be the day of your unit exam, because we'll definitely be done by then. Okay. All right, any questions about the lab? All right then, let's get started on that. Shouldn't take us long to acquire the data. I mean, you're just pulling on a rubber band 5 times. So it should go pretty quick. Okay. All right.